Hello, my name's Kyle. I'm the DevRel at Fhenix, and today I want to go over kind of what is FHE and how to build on-chain applications, how to add privacy on on-chain applications on ETH L2 using just native Solidity. So real quickly, what is Fhenix? We are the first L2 to leverage composable on-chain encrypted private through the use of fully homomorphic encryption. And we're the first blockchain in general to support FHE. So if you want to get started, here's a quick link to the cheat sheet. I think this is pretty useful in terms of like pretty much everything you're going to need to start development in terms of like the faucet, the documentation, etc. So yeah, good place to start. But anyways, yeah, what exactly is this FHE word that's being thrown around? So FHE stands for fully homomorphic encryption, which is kind of a fancy way for a relatively simple to describe a relatively simple concept. It's basically the ability to perform operations on encrypted data without decrypting. So basically, you can do arbitrary operations on an encrypted field without having to decrypt. And so that's kind of the definition of homomorphic encryption. If you think about what you do to field 1 should happen to field 2, etc. And fully homomorphic encryption is the ability to run essentially an endless amount of operations, arbitrary operations on an encrypted field while still maintaining privacy. So sometimes I like to think that like FHE is kind of the new ZKP for privacy. Like FHE is kind of where ZKP sort of was in 2020. Like people, a lot of times it's like the first time you're hearing about FHE. Some people are still skeptical about whether or not it will scale. There's very little, if any, consumer applications, and to the masses, I guess, still considered kind of like a theory or like a concept that is going to be explored. But going over a quick timeline, this concept has existed for a while, but now it's only sort of starting to become commercially viable due to the new generation ASICs, et cetera, and other technological advancements, both hardware and software. But the idea of privacy homomorphisms has existed for a long time and kind of broke into the mainstream, as you can see in 1978 through some seminal works. But again, when you think about homomorphism, it's basically kind of like what you do to one field should apply to the other. And in this case, it's what you do to a plain text field should apply to a ciphertext field. And for about 30 years, there was kind of some improvements to like partial homomorphic encryption, which is the ability to run some operations. Because if you think about how FHE works, it's basically this thing called like noisy encryption, where you're adding noise to obfuscate the truth. And like a simple metaphor for that is kind of like if you're playing poker and you're just going in every single time, right, without bluffing, then if you put down a good bet, like someone's going to know, like obviously you have the nuts or something, so they're not going to play you. So sometimes you need to throw in a little bit of the lies with the truth. And one of the biggest technological innovations in the FHE space happened in 2009. This guy, Craig Gentry, came up with this concept of bootstrapping. And bootstrapping is essentially an ability to kind of checkpoint the encryption, the noise, to essentially make the size constant. And from there's been a lot of like variations and branches in FHE. As you can see, like some use more leveled schemes, which theoretically might be more applicable for something like FHE private machine learning. Which is something that's usually attributed to like ZKML, but like FHEML is probably more applicable. And then at Fhenix, we are currently using the TFHE scheme, which stands for Torus Fully Homomorphic Encryption, which is a library that was created and maintained by a research company called Zama. But our overarching operating system is modular, so in the future, if we need to replace the different operations, that's always an option. So from a high level, what are kind of the differences between FHE and ZKP for privacy? So I'm sure most of you like are familiar with like the narrative, the concept of like, yeah, we should be using ZKP for on-chain privacy. Let's go down that route. But there are limitations to this. And again, the primary one that I said earlier, if you take nothing away from this presentation, is that like FHE allows you to run operations over encrypted field, where like, how would you do that in ZK? You could do it on the client side, but what am I going to like cheat myself? It's like when it comes to the multi-party application use cases, which are necessary for blockchain applications, that's where we really need this privacy, right? Like if you're trying to make a decentralized AMM, multiple people need to be able to like add liquidity, remove liquidity, swap, etc. But as you can see, both technologies technically do provide privacy. However, ZK kind of tackles the privacy by keeping only the committed data on chain and then verifying that computation was done correctly. But again, this, like, if you want to do this in like a multi-party on-chain way, the plain text has to be known because again, you can't run an operation or a computation on this encrypted field without decryption. Which means a plain text copy of this has to exist somewhere in the trace, right? Stack trace. And in blockchain, right, everything that like has happened, there's a trace of it. So if you leaked plain text to memory at some point, that's kind of like a honeypot of getting attacked. And so again, this is kind of good for like single party use, but like, you know, the ethos of blockchain is like multiple distributed ledger in a kind of a trusted way. So like how compatible is that? And again, the benefits of FHE here are like general composability, because again, we're running operations over an encrypted field, and this can be multi-party, as well as each of these can be verified like on chain, step by step, versus like having to go through some like third party service. And so that was kind of just a high level overview of like FHE versus ZK for privacy, just because, you know, that is the mainstream narrative still. But basically for at Fhenix, we try to make it as simple as possible to like use like this encrypted fields in your smart contract state, right? We're not asking you to learn a new language or like have to get used to all these different imports and tooling. Basically, you can just import something simply and use our network. It supports standard EVM opcodes plus our precompiles, which I'll dive into a little bit later. But it sort of works kind of the way that at least I would think that like private state should work, where it's like, okay, what if I could just keep an unsigned integer instead of it just being like open and queryable by anybody who has access to the network? What if it was something that was like an arbitrary bytecode ciphertext that like couldn't be decrypted unless you had the actual like key access or permission to decrypt that? And so from here, right, it's like I said, it's native Solidity. So if you guys want to check it out for the hackathon, you know, if you can use Solidity, picking this up just requires a little bit of different thinking, but syntactically, it's relatively similar. And so there are a few options in terms of like developing on Fhenix. First of all, there's kind of the local setup where we have tutorials for all these things. And also there's links to any specific part on the docs. But basically, this is kind of how you can set up a local image, a local node, basically, so that you can, you know, kind of simulate what the node would look like, or just run the run the network sort of simulated on your own personal device. And although this might be faster, and like ideally you could use it with like other tools that you're used to, I kind of personally prefer Remix just because I feel like I'm a little bit more of a visual learner, and I think it's nice too because you can kind of visualize like what's actually happening, what is the ciphertext formats that are getting passed around, and then what does it actually look like to view this stuff. So again, this is how you would kind of use the Remix plugin. It's relatively straightforward, and then there's a YouTube tutorial, or there's a tutorial video for both of these different plugins. So there's kind of a step-by-step, pretty easy to follow. But think about it like this: if you're trying to pass in like parameters to a function, essentially you kind of have these two options. Both are technically byte data, but basically we have this thing called an in-EUINT8, and an in-EUINT is kind of what you would assume it would be. It's sort of how you pass in an encrypted integer in the form of like this bytecode. But essentially, like, so we support up to 32-bit, but these are kind of the two options that you can use. As you can see, it's like still native Solidity, just the data type itself is slightly different. And the other thing that you have to keep in mind in terms of the design constraints when you're working with FHE, and in my opinion, this is arguably the trickiest part of like contract construction, is the terms of like is branching logic, right? So I'm sure most of us are familiar with like the first example here, sort of that if-else syntax, where we're kind of like, you know, if, you know, A is less than B or something, then let's go down this branch, and if it's not, then let's go down the other branch. But the issue with FHE is that we're kind of trying to operate over encrypted data, so trying to do some sort of plain text, I guess you could say, design for the conditional logic, right? How are you supposed to do plain text conditional logic if it's in ciphertext, because it's obviously going to leak the information. So the lower version here, which is kind of like how we can use this selector function, which is kind of like a multiplexer for kind of assigning a certain slot, and this can also be used to run specific functions. But put simply, basically, we have an e-bool, which is, you know, kind of what it sounds like, an encrypted Boolean. You can't really tell if it's a 0 or 1 because, again, it's encrypted. But from there, you can actually kind of have like branching logic, if you would, where if it is true, then it will go to value. If it's false, it will go to the existing bit in this example. So you can kind of branch logic that way. And yeah, just to really reiterate this point, it's good to kind of recondition yourself in terms of like how we need to develop this code, because FHE is sort of like constant time code where you want to have a single path, because again, like we want to avoid branching, because branching in FHE isn't really feasible. So if you look at kind of like a bad example of how we're sort of used to doing it, versus like a better example is sort of like using this selector multiplexer operation basically to hard to decide which branch we're actually going to go down. So this sort of simulates the if-then logic that is necessary. And again, if you need to run a function specifically, if you want this to actually trigger a function instead of actually just, selecting a value, you can. You just have to make sure that the return value of either of these functions is the same data type that you're assigning it to like the to return here in this example. Yeah, so then require statements. Require statements are also a little bit different when you're working with FHE. And if you think about it, it sort of does make sense, right? Because if you want your contract or a transaction to revert based off of certain logic, if you end up, decrypting that to plain text, right, that's going to kind of defeat the whole purpose, right? Then why even do require? So it's syntactically actually not too different. Basically, you just have to use like an FHE dot require instead of like a traditional require. And in this case, we're basically checking to see that something's not equal. If this encrypted number is basically not equal to 0. So it is technically a little bit different, but for any Solidity devs out there, I'm sure that this syntax will look relatively similar to what you're kind of used to. And then conversion leakage. I kind of touched on this before, but the idea is that we want to avoid leaking plain text to memory, right? Like, because that is sort of how you get in trouble. And if you did it once, sort of, right? Like, I like to think about if it happens somewhere, there's going to be a trace of it, right? Someone, if they dig deep enough, they're going to be able to figure out like what happened. And so this is kind of an example of like passing in an unencrypted integer and then just trying to like encrypt it, right? Because even if you go forward from there and the number is completely encrypted, right? The fact that you at some point passed in an unencrypted integer, if someone were to look at this and like actually dig through and be like, wow, this number was passed into this function at this point and that was encrypted and then blah, blah, blah. You can figure out what number was passed in and then like kind of reverse engineer the operations to get to the point where they're like, okay, now I know what happened here, and then that's like a hackable offense, right? So basically, it's relatively simple. As I showed you guys earlier, how you would pass in an encrypted number, just make sure that you're only dealing with encrypted spaces. And again, that's one of the beauties of FHE, is that you can do general operations over an encrypted field without having to decrypt. And the nice part, again, is that this is all on chain. Okay, so stepping back a little bit from like the contract syntax, just like what is Fhenix and like what kind of are we working on here? So one of our main products is the FHE OS, which you can kind of think of it as like a wrapper. So this is sort of like a high level overview of our network architecture as it exists. So like I said, the actual TFHE RS library, which we are currently using to handle the FHE operations, it's much faster to do in a lower level language like Rust, right? So us personally, we're currently using a fork of the Nitro Prover, part one for the actual performance values, but other, because some of you might be familiar with Stylus, which allows you to add like these stateful precompiles in different languages, as long as they can compile to like WASM execution code. So basically, as long as you kind of do whatever you need to do in Solidity, hit the endpoint, the like hard math operations will happen in this Rust library, and then it will all kind of be broken down into like this WASM code, and then that WASM code talks to our wrapper, and then talks to the client, and that's sort of how the the proof is verified, etc., and like kind of how we have this like L2 structure. But the other thing that needs to be taken into consideration is like, what are the security aspects for the threshold decryption, right? Because we're using threshold FHE here in the sense that basically a call needs to be made to the Oracle in order to handle, and the Oracle here in this case is the threshold service network, which you can kind of think of like the multi-party compute key management network that kind of handles whether or not the actual decryption is valid, or if it was if it was meant to, if the actual what's being decrypted is actually able to be decrypted. So those are kind of like the main aspects of sort of how it's working, kind of from a high level. But yeah, so I went over kind of how the contracts work. As you can see, it was pretty similar to like native Solidity. And then how does it work on like the client side? So we try to keep it as simple as possible in terms of the developer experience. So basically, there is like this thing called the Fhenix client, which uses Fhenix.js. Again, there is documentation and a bunch of code examples on our docs if you would like to take a deeper look. But basically, it's just a way of kind of formatting something. So as you can see, you pass in 5, and then basically it will encrypt it as an int5 in this case, kind of like generate the ciphertext with a plain text value of 5 in this case, and then you can just use that to interact with your ABI. So integrating your ABI is still it's still basically the same thing, except the values that you pass into the functions themselves that gets passed into the ABI, the contract. It's just like one extra step here. So again, as you can see, it's compatible with ethers. And so, you can use the tools that you are familiar with using. We're not trying to reinvent the wheel here. We're not trying to expect you to kind of like learn a new language or use an alternative tooling. Like ideally, we want to make it as simple as possible for you guys to just, do what you're normally doing with Solidity. Like I said, we support the standard EVM opcodes. So if your code will run on like a standard EVM, it'll run on us. But you actually get these extra functions. And so that brings me to permissions, which is the other thing that the Phenix.js can help you handle. But permissions are put simply, it's basically like there's encrypted data. But at some point you want people to actually view the encrypted data, but you only want some people to actually be able to view the encrypted fields, right? Like if you're playing a game of FHE poker, right? Like I want to be able to see my 2 cards, but I don't want the person I'm playing to be able to see my 2 cards because, that defeats the whole purpose of poker. So basically you can think of permissions here. It's kind of like, a sort of a version of like EIP 712 in the sense where it's kind of has this segregation where, syntactically, as you can see here, we're passing in the permissions object, to the actual function here. And then we have this, like, you could think of it as like a modifier, this only sender modifier that essentially checks to make sure that the person trying to request access to view this data, the message.sender, if you would, has the correct public key permission to view it. So basically, only the person that's actually requesting to see this data has the correct key access to see this data. And from here, you can add a lot of different conditional logic, such as like, okay, hey, maybe I only want person A to see person A's cards, etc. And so here's just kind of like a quick example of how this could be applied to a simple like ERC20. And basically, I think that, some might argue that like, maybe FHE is overkill for like privacy. And sometimes if it's something simple, like just a token transfer, you could just use ZK. I would argue that like, if you want to run conditional logic off of that, make a more like more complex sort of application, then how else could you really do it? Because just using on-chain ZK, if you would, it would require, again, decrypting to run an operation because you can't run an operation over an encrypted field, which obviously leaks plaintext to memory. And then like the major vulnerability. So again, kind of just wanted to kind of run over just a really simple sample contract. And again, if you want more specific information, there's a lot more examples of different natures on the documentation. But basically, I just kind of wanted to exemplify like how straightforward and how few steps it actually can be to add these encrypted fields to your contracts, right? You don't actually have to go through a different language. It is Solidity. So hopefully the learning curve, especially over the scope of something like a couple-day hackathon, I think is like, ideal amount of time to kind of experiment with this technology without having to like go through the process of spending like the first day and a half, like just figuring out the new syntax and language, et cetera, and the environments for everything. Speaking of the hackathon, so Phenix, we have a 5K hackathon prize. So in order to be considered, you just have to submit a full stack application, which, really basically just has those 2 parts. And then we're looking for a project that, can show a creative use of FHE. If you think about why do we need privacy? How is composable state privacy different from like point of attestation privacy that you might be able to get through other methods such as like ZKP? But in general, I think the important thing is just to work on something that you find interesting because, that's kind of where the cool use cases are. And a lot of people will say that like, oh, FHE is slow, blah, blah, blah. Like I said, it's kind of like where ZK was years ago, but it is, scaling a lot faster than I think people realize. There's a lot of different methods. Like I said, it's still kind of like the pre-ASIC days, but the ASICs are coming, hitting the server farms relatively soon. And so, like I said, like when it comes to the actual computation throughput of FHE, versus maybe like other methods of running operations over encrypted field, FHE doesn't require these extra interactions, right? Which again, even if you're going to do like some sort of like on-chain rock, paper, scissors, something that requires asynchronous inputs to advance the state synchronously, if you're to use ZK, it would require some sort of like preimage/knots. And then essentially like that has an extra interaction that also requires the user/the client to like keep track of this knots or of this key, if you would. So like, why go through the extra steps to have why go through the extra steps for privacy to get less of a composable state? That's kind of like my 2 cents from a high level. But yeah, in terms of general runtime tips, like I said, FHE allows you to run these operations, right? So you can have an add operation, a multiplication, division, selectors, less than, etc. And so the thing to keep in mind here and remain cognizant of is that certain operations are more expensive than others. For example, as you can see here, adding two numbers is going to be a lot cheaper than like dividing two numbers. And going along the lines of like how FHE is scaling, even as recent as like December or January even of 2024, the concept of running ciphertext over ciphertext division, even for an 8-bit encrypted number, was, kind of considered like infeasible. But now, like recently, we've seen things of like people being able to run multiple 32 over 32 ciphertext divisions in a single transaction. Something for like if you wanted to encrypt the invariant for like a V2 clone of Uniswap, for just an example. But as you can see, like the other thing that needs to be considered other than just the operation itself is the actual like size of the plaintext, right? So, using an EUINT8 number is going to be a lot cheaper than using 32 or anything larger than that. So basically, those are kind of like the main design constraints that need to be kept in mind. And, worst case scenario, if you kind of get stuck in a situation where you have, you kind of just like want to try out ChatGPT, I think it's actually, it's actually surprisingly pretty good at just coming up with like a quick implementation that you can try. And this comes straight from our core developers. They're suggesting this. So, I definitely recommend giving that a shot. And that's pretty much the presentation. If you guys want to try a more code-along example, you can try this blind auction that was created by another one of our devs. I think it's kind of interesting because it goes over some of like the nuances of like design constraints, handling overflow, figuring out the ways to optimize different selector and branching logic. So I definitely would recommend checking it out. And I appreciate your time. And if you have any questions, especially pertaining to the hackathon track or FHE in general, or feel free to talk to me, reach out to me on Telegram, or I'll probably be around for around the event. So thank you for your time.